Okay, we have sets here. Got it. Okay. Good.
Good afternoon. This is Ronnie Chaudhary. I'm the director of Center for Connected Multimodal Mobility. It's my great pleasure to welcome Dr. Taiber. He's the founder and managing director of IAMTS. He's actually he's my mentor for many years, and I learned so many things from him. I hope that you could learn a lot of great things from him today. So, Dr. Taiber, I'm glad to welcome you to our distinguished speakers talk today.
Thank you very much, and I learned so much from you too. So that's that is very balanced situation. So thank you very much for coming to this lecture, and thank you for the kind introduction. So today I wanted to talk about the topic of highly and fully automated vehicles and how we bring those vehicles into safe operational deployment, and also how to make how do we get them into regulatory compliance. So before I go into the details of this topic, I wanted to give a little bit personal background about myself. So I'm originally from Germany. I started my career in the automotive industry with BMW Group, which has a major presence also here in South. So is it now working?
Yes.
Okay. So as I said, so I started my career with BMW Group, and I was involved in the early planning stages of COI car more than 20 years ago. And then in this picture, you see on the right-hand corner, the BMW IT Research Center, and which is an IT innovation center. And I was directing this center for a number of years, and then moved one house further to the graduate engineering school and served for a number of years as a research professor. And then during this time, I actually worked on a number of quite interesting research projects, which typically were centered around connected vehicle technology, vehicle electrification, and infrastructure to vehicle interaction. And then during the time I worked at iCar, I also started focusing on developing a test site for transportation, which is called ITIC, International Transportation Innovation Center, which is just 5 to 10 minutes away from COI car at the Donaldson Airport. And so for the last 20 years or so, I was very focused on this environment. So what I wanted to first introduce a little bit the terminology that is being used in context of automated driving. So what you can see here are the different levels of autonomy. So if you're driving the car in a good old way, and basically without any assistance, then you would have a level 0 vehicle. And once you have the capability that the car really can completely drive itself, then we are entering what we're calling level 3. So that's when you really, the vehicle is predominantly machine operated and not human operated. So level 3, 4, 5 are all under basically dominant machine operation at 3, and then fully operated by the machine at level 4. Now, when you have a level 4 vehicle, you could still, under certain conditions, decide I still want to drive the vehicle manually. So you have pedals and steering wheel in the car. And if the car is like in a train, you don't see any steering wheel, no pedals, then you're definitely on level 5. So this helps maybe a little bit in their classification of those automation levels. Now here, this is a chart from the Society of Automotive Engineering, where that is further explained. So what you see here on SAE level 3, that when the vehicle has a problem and cannot actually be operated any longer by the machine, by the computer, then it will request the driver to take over. And so that's important to understand when we talk about level 3 systems. And then what is also important is to give you some examples of vehicles that are highly or fully operated, automated, operated. So on the left-hand side, you see a GM Cruise vehicle. This vehicle has no steering wheel or pedals, and it's being used as a shuttle. And this car is planned to come out soon on the market, as far as I heard. And this is an example of a basically a level 5 vehicle, right? Now, one of the issues you will have, and I will use the term operational design domain. So operational design domain basically defines under which conditions and on which street network the car can be operated. So you see here blue sky, sunshine. As soon as the environmental conditions are changing, let's say heavy rain, snow, ice, it could be that you cannot drive this car at all because it does not meet the conditions that it needs to meet to be operational. So so that's where the limitation of level 5 is. You always need to define exactly what is the operational design domain, what are the conditions when the car can be operated. You see here on the right-hand upper corner an example of a Waymo car. This is basically a retrofitted hybrid car from Chrysler with additional sensors and software from Waymo to make it level 4 capable. So it has a steering wheel, it has pedals, and typically there used to be a safety driver in the car. As far as I know, they have now allowed to remove the safety driver. You can actually go into this car without anybody else in it, and use it as a level 4 vehicle. The lower right-hand picture is a Mercedes, and this is a level 3 car. So in this situation, you see a simulated highway situation. And basically a few seconds later, then the driver would be requested to take over. So that is a level 3 situation. So I just want to give you some examples that you get an idea what it means. Now, if you look into China, for those of you that you deal with maybe Chinese manufacturers or companies, they have a little bit of different terminology. Like you see, level 3 means conditional automated driving, and then level 4 is highly automated driving. So they use these terms different. In US, we would consider level 4 as fully automated driving and not highly automated driving, and level 3 as highly automated driving. So there are some differences. And what makes it interesting is you see that they also are classifying the infrastructure side from level 1, 2, and 3. And what they mean with level 3 is that the latency to the backend is so low that you can actually delegate safety critical decisions into the backend. This is at the moment not possible, but you can imagine if you have limited computing power in the car, or the car is being used for many years, so you cannot constantly upgrade the hardware capabilities, but you can upgrade the backend with more computing capabilities to cover more complex scenarios. They have already in their terminology considered the case that then you could delegate safety decision control into the backend, which is very forward-looking, right?
What in level 3 of the Taiber, so the infrastructure playing a role?
So we are talking about this level here. So level 1, 2, 3. Yeah. So that's the infrastructure side.
The highest level, then level 3 infrastructure.
That's the highest level. So that's the lowest level. So this would mean that, let's say you get from a sensor in the road like ice warning. That could be this one. This is just an auxiliary information, but this is in real time. So the latency and the connection to the backend is so tight that you can actually make safety relevant decisions here, but you cannot do this here.
What's level 2 then? What is feeling so?
That is the collaborative perception is perception. Perception is just giving you additional sensor information in real time to the car, but it's not making a decision. It's just perception. And then the decision here and the control would be in the backend. So that's kind of the difference. And you may agree or disagree with this. So this is from the Chinese perspective. They have certain predictions how quickly level 2 and 3 is coming into the market. I think my personal opinion is this is too aggressive in the timeline. But you see in general that level 4 vehicles are just entering the market in 2025, most likely first as robotaxi in geofenced areas, and then by 2030, you have much more of those vehicles coming into the market, and then level 2 and 3 would be quite commonplace according to these predictions. And these predictions are pretty new from August last year. Another roadmap that I think is important to look at is the V2X roadmap. So this is from the 5G AA consortium, some estimates. And what you can see here in 2024 and 25 is automated valet parking and teleoperated driving. And so Mercedes, to my knowledge, they just got the certification for automated valet parking, and there are like Waymo that I mentioned, where in the vehicles that remove the safety driver typically have a teleoperation capability. There's also for 2024, you have vulnerable road user collective awareness. There's a lot of work at the moment hitting the marketplace where more attention is being paid to recognizing vulnerable road user, bicycle drivers, scooters, and people that are walking. And for 25, 26, you see there's some first work in cooperative maneuvers, which would also support cooperative driving, which requires some standardization of data exchange between the cars of different brands. And then up to the end of the decade, when you can actually have dynamic cooperative traffic flow. So I think this roadmap is still pretty accurate in terms of their timing and assumptions. Now, this here is an example of a project that is currently being implemented in Michigan by Covenue, which is a company from Alphabet. They are equipping lanes with specific sensors to support highly automated and fully automated driving. And I think this is a good example where the vehicle manufacturer and the road operator are going into a closer collaboration. So you see this here in the system architecture picture. The interesting thing is with this approach, you don't need to wait until all the vehicles are L3 or L4. So if they are L2 plus, which means they have a little bit more capability than just L2, you can create a platoon of the vehicles that feel like you're driving autonomously. So that's pretty interesting. And I just wanted to mention this development also. And by the way, you can interrupt me at any time. So if there are questions, because I cannot most likely cannot memorize everything until the end of the talk. So, so the other thing is what I want to mention. What is IAMTS? What does this stand for? So IAMTS stands for International Alliance for Mobility Testing and Standardization. The inspiration came through the work at ICAR and ITSC. We had actually in 2018, there was a SAE conference at ICAR where we had a workshop. I was moderating this workshop. Different test companies and suppliers and OEMs were present. And we had a discussion whether we need a consortium to talk about how in the future our vehicles, in particular, highly automated vehicles being tested, because they need to be tested in a little bit different way than traditional vehicles. And so the idea of IMTS was to anticipate these regulatory and technological challenges and then come up with a roadmap approach and related to testing and standardization. And in particular to deal with these level 3, 4, 5 category of automated driving. So that's how IMTS was originally created. So the strategic goals of IMTS is to make it easier to introduce those vehicles to the market. At the moment, there's a lot of setbacks. You heard that some companies are pulling out of automated driving because they don't get enough traction or they don't make enough progress. Even Tesla has a lot of challenges with their autopilot or full self-driving vehicle, although Tesla will always say the next 6 months we have it fixed. But what I think is important, IMTS is trying to bundle the knowledge worldwide to give a framework and to give some guidance to the companies and the research people that are working on it to come to a solution that works. And so what you need is a mix of virtual and physical testing methods in the right environments. So we will give guidance on how much simulation, how much physical testing is needed for which situation that you want to master with automated driving. We also are helping to define the capability side of the test beds. And cyber physical means that you are combining virtual testing with physical testing, which also includes security aspects, not only the safety side. And there's even we are currently revising our strategy that we are also looking more into sustainability goals, not just safety goals and security goals.
I just have to
yes.
Question here.
Yeah.
So when you talk about certification, so
Mm-hmm.
so it's related to safety, cybersecurity. And you mentioned that there will be another criteria on
Mhm.
sustainability. So what are the safety, cybersecurity? So what will be the different criteria?
So give me a little bit. There is a lot of slides that cover that. So let's come back to that. So then what is basically the identified challenges is that you need. So if a company has a lot of simulation tools, the problem is that it's not enough that they believe in these simulation tools. It needs to be that the governmental side, the ones that basically have to approve that this vehicle can be operated, they also need to have trust in these tools. And I will give some examples later. So if your simulation model is not precise enough, you always have to actually validate the system in a physical environment. And the better you understand the physical environment, the more precise the model is, then you can do more and more over time with simulation, as we know from crash testing, where 20 years ago, you had to crash much more cars than today because you have better simulation models, and these models are validated with physical testing. So the other important topic is that automated vehicles will not, from one day to the next one, all be at the same time at the road. It will be kind of what we call a mixed fleet. So there's coexistence of non-automated and automated vehicles, and automated of different automation levels. So the problem is, because this mix, the ratio will constantly change, you need to, the system response is changing. And so you have constantly to think about adapting the algorithms, because if you are surrounded by automated vehicles and they are not driven by humans, you have no irrational behavior. You basically know exactly how they behave. But as soon as there's a few humans there and they get crazy, then you have irrational behavior, and the algorithms need to handle this situation and have to allow a safe operation. And that is actually the key challenge, right? So, and then the other is also that we are going through different levels of connectivity at the moment. A lot of telcos are rolling out their 5G networks. By the end of the decade, you have 6G. So you always have some differences in the connectivity quality, and that is also different for different regions in the world. So there, you cannot just assume because I can stream my audio nice on the I-85 that this works somewhere in the mountains in the same quality. And so there these changing levels of connectivity and have to be considered also. So our response is to compare different regions in the world in terms of what is similar. So what are traffic scenarios or driving behaviors that are similar and which is different. So we all know that in maybe here in Clemson, somebody drives different than in Turkey or in Bangladesh or whatever. So there is differences, and we need to understand those differences. And so the other is that different countries have different regulatory approaches, but if you are a car manufacturer, you are selling in all these markets, so you need to be aware of where the differences are. And then if you have, in the old days, the companies had one test site for US, one test site for Europe, one test site for China. This is changing at the moment. You can, in cyber physical testbed, you can, for example, create in the US, you have a cyber physical testbed and you create a situation in Italy, maybe. So you don't have to do all the tests in Italy. You can actually create that in the cyber physical environment, and it saves you money. And so there's a change in how you build those testbeds. So we are looking globally at the best practices of these test methods, but also we are looking at the different test sites. We have a database where we are describing all the different capabilities of those test beds as far as we learn it. And I want to mention that some of those test beds are extremely expensive to build. So some like this one on the left side is basically $500 million, right? So it's similar to semiconductor foundries, you know, where it's very expensive. So as soon as you have a large physical sophisticated test site, it's an extremely expensive asset. And we cannot have every car company build another big proving ground. So at the moment, times are changing where you are have more and more proving grounds that are used by more than a company and are shared. And ITSC was one of the first proving grounds where that shared user concept was applied. And in the meantime, we know that this concept has been adopted by many others. So what is important is the understanding of the limits of modeling, which I mentioned before. So for example, on the right-hand side, you see a sandstorm, or you see on the upper right-hand side, a snow, so a foggy situation in winter condition. And there's always limitations how much the simulation can map these real solution or real conditions in the model. And then what sometimes is interesting, let's assume you're driving in the Emirates and you have a sandstorm. You want actually to now the physical car that is driving in the storm should be connected to the model in real time so that you know the behaviors. You can actually compare. So you measure the sensors, how the car is at the moment behaving in the physical location, and then you compare with the simulation, and then you know how exact the model is on or what has to be improved. So we have different work groups in IAMTS. So in particular, at the moment we have 5. One is more focused on what we call scenarios, and I will talk about this in a moment. We have another work group that looks into capability of test beds, another one that looks into simulation models and how to correlate them with physical testing, how precise the simulation models are, cybersecurity testing, and also life cycle compliance. That means, is the car, when the car has a software update or a hardware upgrade, is it still compliant to the government regulations? And typically it's not, so somebody has to kind of give you an approval and you have to show that it's still compliant. So the way the work groups work, they have different experts in it, and there's one work group leader. So we have different companies or organizations that lead the work groups. And then we have in total at IAMTS more than 300 experts gathered. And it's still growing. So we hopefully we will get to a few hundred more over the next 2-3 years. And then we have a really big brain power of experts, and they can then bring their best practices into the work groups, and we publish papers, and we are organizing events and conferences and webinars to disseminate the results. And I would like to invite Clemson also to join as a member. It's very inexpensive for universities to join, and it's for students and researchers a great way to be internationally connected and to find out which are the leading edge topics to work on. So I think it's a very good way to learn. So in ecosystem testing, there's some interesting insights. So I grew up in Munich, in Bavaria, in Germany, and my house where I grew up is maybe maximum 5 minutes from this site here. All right, so it's a huge BMW proving ground. And the interesting thing, this proving ground, when that was designed and built, all they wanted to do was testing brakes and durability of the vehicle, and it was all about reliability of the components in the car, right? And now the site has further developed, but it's still very vehicle-centric. So on the right-hand side, there is AVL Zalazon test bed. This is a brand new test bed in Hungary. which costs hundreds of millions of dollars or euros. And we had our first symposium there last year. And what is interesting, they created a smart city, similar to what you may have heard from Michigan in the American Center of Mobility. You can actually test networks. You have all kinds of different road configurations, intersections, highway, and all kinds of that, which you would not find on the left-hand side in the BMW Proving Ground. So this is and the BMW Proving Ground is only used by one, and that is BMW, whereas the Zalazone Proving Ground is used by many different companies of the ecosystem. And then what you see then below that is the idea that you can not only test one car, but you can test also vulnerable road user interaction. You can, and what you see in this picture here, you can also test, which is ecosystem testing, multiple vehicles that are going into complex scenarios, and you see their behavior together. So from focus on single vehicle, just single company, to multi-company, multiple vehicles, different types of objects. So that all happened in the last 20 years, I would say. So I had the privilege to work with a company that is leading in building these proving grounds and test sites. And what they told me basically is it started with determining, okay, which road types do we want to cover, which traffic signs, weather conditions. And then it went into what we call edge cases. The problem is that if you're going into certain edge cases, even with the best trained safety driver, it would be too dangerous. So you have then at some time you have to go into the simulation environment, because then you can explore more of those edge cases in detail.
Edge cases in extreme cases.
Extreme cases, yeah. So where you go to the, basically that could be situations where you definitely crash. So what they do in the meantime is they have these soft target vehicles. You can crash into the vehicle, but I'm talking now about where somebody drives totally crazy, and they want to see, I mean, even with the soft targets, you need to stay in certain boundaries. Right? So, so this kind of moved from physical testing more to, I would say, mixed reality testing. This picture here shows it a little bit. So most of the car companies are using the V model in their development cycle. So that means they start with functional requirements, system requirements. Then they start programming the software, designing the hardware. And then you get to a point where you bring all the different components together. And when you bring the different components together, so this is more basically designing the different components in detail and then integrating them. And then you have to make these validation tests, whether all the different components are working in the right way together. And then when you go into serious production, the problem is that you are improving certain components, whether it's software or hardware, and then you would have to do more integration testing, right? So, and that is typically the difficult. So you normally do not really want to touch a vehicle when it's in the market. But in the meantime, with like what we all know from our smartphones, we constantly have updates, system upgrades, same with the car. So you need to do more integration testing while the car is already in operation and in the market. And so
when it's actually driven by public, you do the testing at that time in the market that it's already.
Yeah, so what you do is that, so let's compare it. Let's say when you do your next iPhone upgrade, before you can actually upload the software over the air, it has been tested, right? So it needs to, there needs to be some conformance testing for that. And that's what we don't want is that we test while a user is driving the car. So, but when he updates the software, we want to make sure that that update has been properly tested and validated. So that's what I'm talking about. So here, what you see, and I wanted to introduce the term homologation. What does homologation mean? And it's not used in all markets in the same way. So basically, what you see here is if I'm a car manufacturer and I'm starting to design the car, I have to, and let's say the car should be self-driving, I have to test a lot of scenarios. I have to create a lot of test cases. I get to know the system better and better. So now I can reduce the number of test scenarios and test cases. And when I'm getting to the government approval side, which is basically the homologation, so I have done my core development work. Now I want to sell the car, but I need a type approval basically. And so now the government wants to see not all the test cases I have done originally, but a certain number of test cases. And in Europe, there's a very important difference to the US. So in Europe, when I want to bring the car to market and I go to the government says, I want to have a witness, that basically a third party that is authorized and licensed to do these tests and tell me, the government, that this car is safe. And that's called third-party certification. In the US, in the automotive sector, there's self-certification. So that means that, let's say if you're GM or Ford, you tell the government, this is what the car is able to do. I have done all the tests, and here's the documentation that I have done all these tests. But and then if there is a problem, this is the key issue. In the US, if let's say they did something wrong, there's a product liability risk. So they could be sued for a lot of money. But in Europe, once you are through the government homologation, something happens, they cannot be sued because the government said this is safe to operate. They could still be potentially sued, but it's much, much more difficult, and it would be much less money than in the US. And so there, as I said, and in China, the system there is similar to the EU or European system, third-party certification. And but I wanted just you to get a feel what that means. Now, in the old days, when the car didn't have a lot of software updates, let's say you have a 10-year-old car, you are not constantly daily update the software, but this could happen in a very new car. So what happens now with these new cars is that if there's a lot of software updates and you want to make sure that you're not going through all the tests like here or here. So you just you say, oh, I improved a feature in the car. And then you say, okay, I show that this feature improvement has maybe could have some side effects, but I'm going through all the tests to show that there are no side effects. And then go to the government, and I do this purely virtual. I just do this through simulation and not through physical testing. So, and here's it's explained. So the idea here is the manual type approval is extremely costly, could take a long time. There's a lot of manual paperwork to do. And in the new setup, you have simulation only, and the government understands, okay, these are the software tools you're using, they're validated, I trust them, and if there are these data, then and the numbers are okay, then I give you the new approval. And then you go through incremental updates. Yeah? So this here is from Audi. They are a strategic member at IAMTS, their view. So you see, you have in the development vehicle testing in controlled environments. You have vehicle testing in the real world. field monitoring means these vehicle testing, these are still cars in development. They are prototypes, and field monitoring are vehicles that are being sold. So their customers are their real customers. You look at the data and then you do a virtual assessment, and you are basically feeding the data lake from all portions. You can also do virtual drives and just test the system behavior in maybe extreme scenarios that you wouldn't do in a physical environment. So for them, sorry, I lost my microphone, so I'll get it back to work. Okay, so they want to standardize the driving scenarios, the V2X test infrastructure. Cybersecurity compliance is very important, and to test in a combination of physical and virtual testing, and then enable virtual homologation in over the life cycle. This is for Mercedes. You basically see that they emphasize complex scenarios with many different traffic participants, which I have shown before, and then also more weather-related problems. So very often the problem is, how do you simulate certain weather conditions, and border between physical and virtual testing is blurring. So IAMTS is an alliance of organizations. We have all kinds of members, test organizations, car manufacturers, engineering service providers, small companies, test bed operators. They are from different parts of the world. And we are further growing this organization, and its headquarters in Vienna. So I have to be in Austria quite a bit, and it's operated out of there. So now I wanted to give you a few examples. So one of the first example I wanted to give you is what we learned from the crash from Elaine Hatzberg with an Uber vehicle in 2018. Who heard about this? Did anybody hear about this crash? Or is it new? So what happened was that a couple of years back, there was a big hype for autonomous driving. Everybody thought 2020, everything is autonomous, right? And so, and Uber with Volvo had an alliance, and Uber at the time was talking, we will kick out the manual drivers of Uber and we're getting all autonomous. And in this hype situation, there was a little bit a lax behavior of testing the car. So what happened was, this car here is a test car, so it was a prototype, and it was driven in Arizona on this road. And there was a lady crossing with a bicycle. So she was not using the bicycle by biking. She was actually walking with a bicycle to cross the road, but she didn't use a pedestrian stripe. So she just did it somewhere. So what happened was that you have a safety driver in the car, but what happened was that all the systems to detect her failed, and the safety driver was watching Netflix, not paying attention, and the woman was killed, right? And so, and here, what I wanted to show you what exactly happens, because it's interesting from an engineering perspective. Keep in mind, there's a couple of years back. In the meantime, systems can do more. So the radar detected the lady 6 seconds before the impact, and then there was the LiDAR then detected it. The radar detected her first 6 seconds before, then the LiDAR. But the classifier, so the object classifier, could not detect what it was. So it just said this something, but we don't know what it is. And then what happened was that 5 seconds, so the next from 6 seconds, okay, before impact, the next 5 seconds, system alternated between classifying her as a vehicle, a bike, or an unknown object, back and forth, right? And then inaccurate classification. And then when the car thought it's a vehicle or bicycle, it assumed she would be traveling in the same direction as the vehicle, so going this way, but in the neighboring lane. And when it classified as an unknown object, it thought it was static, but it actually was crossing the road, right? So then each time the classification flipped, the car treated her as a brand new object and started from new, right? So, and then it couldn't track what it was doing, and then did not slow down. And then the braking system had been disabled because there was a radar interference. Okay. And which is crazy. And then they said now the vehicle was 1 second away. You see here 1.2 seconds to impact. 1 second away. Then it realized that it could not avoid impact, and it could have still slammed, but the system called an action suppression in. And that was because they said unnecessary extreme maneuvers for false alarm. So it thought it was a false alarm. Okay, and then it suppressed braking for a full second, and then simultaneously alerting and handing control over back to the safety driver. And then the safety driver was watching Netflix, couldn't do anything, was distracted, and it would anyhow be too late. But normally, the safety driver should have seen that something and already said, "I'm taking over," right? But you can see what can happen here. So the NTSB investigated this case very carefully. This is from a presentation from Audi, which was recently held through IAMTS. And what you see here is, and what was in the example before, the unintended system behavior. So you can have either a false positive, so that means system intervention in no critical situation. So I was told by some developers that said, we're driving on an empty highway, and then the car goes in emergency brake, and nobody knows why. Could be a leaf, could be a bird, who knows? So that would be a false positive. Or no system intervention in a critical situation, which is false negative. In both cases are bad. I mean, this is, there's no critical situation, so you don't harm anybody, maybe just a driver, but in this one, you can actually kill people, right? That's what happened with the Uber car. So I just wanted you to kind of be aware of those situations. So that's a challenge. And another problem I wanted to touch base on is the test complexity. So we have a very complex system, many sensors, complex software, and we have a complex environment, complicated traffic situations, complicated weather conditions, irrational behavior from drivers, and so forth. So everything comes together. And the question is, how do you deal with this complexity? And this here shows a little bit an approach. You need to prepare the tests. Typically, you need models, you need scenarios, and then you need so-called test cases. And then you go from the test cases into the simulation. You either test it completely in the simulation or in hardware-in-the-loop systems. You can also do it the other way around. The human is actually driving the simulation model, vehicle in the loop, or an improving round, and then road testing. And here is an example. This is one of our members, like AVL, it's a larger engineering service company. What they do is they generate scenarios and they extract scenarios from real world driving, and then these are generated and they're all brought into a scenario database. And then they generate the test cases, and then they allocate the test cases to simulation driving cube, what they call it, hardware in the loop, basically improving ground. And so what is important in terms of type approval. So Germany was the first country in the world, to my knowledge, that has that started a law, was passed, I think, last year, where you can say, I want to drive the car autonomously, and I want to go through a complete process. And the government should then give me a stamp. And nobody has got a stamp in L4 yet, but at least the law is there and the regulations are there. And so what you are doing is you need to bring different aspects together, and then different government authorities. So the federal authority KBA, which is like the NHTSA of Germany. So they're on top. And then you have the road authority, which, and then you have the local authority. And what that basically means is, so in Germany, there is something that, so there's a ministry that is responsible for the roads, like US DOT, right? Then you have a ministry that is responsible for type approval. And then you have a local organization in each province of Germany, where if you get a driver's license, you need to go to them and get your driver's license. So the law basically requires that you tell the government exactly where you want to operate the car. And if it's operated in the whole of Germany, you would have to go to every single state of Germany to get approval. So there's a framework, but they still need to get it. So it's a kind of a federated system of approvals, right? So it's pretty complicated.
They are certified in one location.
Yeah.
Can they drive in a location, or they have to get all the certifications?
Now, what they will, so I will show you the process, but the way it works is you do one application with the KBA first, right? And to tell them, okay, these are the scenarios that I'm doing. This is the road network. And then they will say, okay, show me the scenarios, show me that it's safe to operate under these scenarios. And then they will tell you, oh, you have to go to this state and this state and this state because you want to operate the car all there. And then you have to get their approvals too. So that's kind of how it simplified speaking. I will come to this. This is separate, okay? Now, this complicated chart here is from the EU. So the EU, the European Community, adopted the German law into EU law. And this is still at the beginning. This is not yet fully implemented. But basically, what I explained for the states in Germany has also to work with every single country in the EU. And there's only one country at the moment, it's Germany, that has that legislation, has some experience, not much. The law is now on EU level, but now every single other country has also to learn how to apply these rules and how to go through the approval process. Right? So this will take years, most likely. Now, to give you a rough idea how this works, so you are, there's critical scenarios, there's nominal scenarios, and there are road traffic rules. And so what does that mean? And then failure scenarios. Failure scenarios is when something goes wrong, right? So, and you want to know, okay, if I'm losing the sensor, what happens with the car? You know, so that would be a failure scenario. Critical scenario, what happens if somebody cuts in and I'm getting to an edge of maybe I'm colliding or not. So that would be a critical scenario. Nominal scenarios is just normal maneuvers that happen. And then road traffic rules can differ from country to country, right? So you make sure that in one country you maybe, like in US, you can, I think, pass on the right-hand side, but you are not allowed to do this in Europe. So it's, for example. So, what is important is also what I mentioned before, the virtual tool chains. So the fidelity level of the tools are very important. So the government will not tell you you can only use this software or that tool, but they will say, we want to know that this tool that you're using or the tool chain has this fidelity level and is able to do this and this and this with this precision. So, and IAMTS will give them the validation that to the government that this can be done. And we have developed a paper where this is described in more detail. So then the other is now the cybersecurity. So this important is, and this is only in the European community, this is R152, okay? So this is the UNECE regulation. And it basically says it's mandatory for all new vehicles from from last year that this regulation is met. And it will be mandatory for all new vehicles produced from July 2024. So the way that works is that all the suppliers from tier 3 to tier 1 to OEM have to show that they are compliant. And then the OEM has to go to a technical service, which can be a TÜV organization. All the technical services are in IAMTS. So they are listening to us, you know, what we recommend. And then the technical service goes to the government and says, okay, this is compliant. And we have a work group for cybersecurity, and they just were doing all the interviews with industry. Which tools are you using? Are you already compliant? Do you have problems? And then we are collecting this and then reporting it back to the government. The other thing is traffic regulations. So I just want to mention, we have one of our members, Control. They are doing the work of taking legal texts, which are text like Word text, and bringing them into a mathematical model. And that's very difficult because there's different interpretations possible. So there needs to be an exchange between the lawyer and the engineer to say, oh, did I really interpret this correct? And is this model correct? And then if so, then this will go into a rule which is being used by the vehicle to make sure that in the automated vehicle that it's compliant to the traffic rules. And that's another challenge because there's a lot of rules. And then life cycle compliance, I just want to point out that there are PTI inspection, periodical technical inspection, PTI, and they will test the vehicle. So for example, if you had a crash with the ADS system and you didn't repair it, the system malfunctions. So some people, and it can cost thousands of dollars to repair it. You don't want, because maybe it was your fault. You don't want to spend the money. But then in Germany or in Europe, you will be caught by the PTI because they're mandatory inspections. And then they will tell you, okay, you are not allowed to drive this car any longer for this automation level until you have fixed it. Right? So that's very important. So we have also work on this. And then finally, and I'm nearly finished. So the key steps is we are trying to establish a platform of common understanding where we are going into the regional aspects of driving behavior, infrastructure, safety, security regulations. So we're looking in this in all markets. We are recommending a network of cyber physical test beds, which are accepted by the regulators. And I think the US are currently behind. Europe is leading here. So, and China is also a little bit further ahead. So there's a lot of work in the US to do and to catch up. And then we are doing the audits and certification of whether these test beds are having all the capabilities they need to have so to be used by the government. We are, as I mentioned, so we are currently starting this certification program. So it's a certification scheme for cyber physical test beds. So I will be in Berlin in 1 week from now, where we have this workshop with key experts that will gather to discuss this. can also join virtually. And so what IAMTS is doing is we're bringing these different experts together and the organizations. We are doing best practice development, and we are basically doing certain aspects that are non-competitive. So our emphasis is non-competitive, but some of our members are then taking the knowledge and then bring this into competitive aspects. And then orchestration of the regulatory and environment. We are also helping develop international standards, and we are defining the certification criteria for the test infrastructure. So that was it. So I hope I gave you room for some questions.
Any questions?
Yeah.
From the audience? Online audience, we can here we can ask them to write the question in the chat box.
Just 1 minute too late, so it's just me.
Perfect.
Okay.
My question is about the certification.
Yeah.
For the US, you say it's very hard here because they don't have third party.
Yeah, so the problem here is that the tendency is that every OEM is doing it for himself under criteria that are not standardized, right? So when GM or Ford or Chrysler has their own test sites for Tesla or Apple, I think Apple is also working on it, and they will not share any information. What in Europe happens is we are not forcing the OEMs to share information, but we are saying, if you want to prove that this car is safe, you're not doing this on your proving ground. You're doing it on a test site that is certified and accepted by the government. Only because then we can ensure that we know exactly what capabilities are there and not what you claim you could have. So, but because these scenarios, we noticed that when I talked to Tilke, which is the company that is building the proving grounds, they said, oh yeah, this OEM built the intersection this way and covers this scenarios, and then the other OEM did it in a different way, and they're not compatible.
Standardized.
And so not standardized. So now when those cars are meeting each other, and so in a standardized situation, you say, okay, I'm firing this scenario. How do you have that too? Yes, I have it too. And then you know exactly what happens. But well, I'm doing this scenario. I don't know what your scenario is, and you don't tell me what your scenario is, so I have to guess what your scenario is. Then you have a problem. You saw that in the Uber case, you know, where they're going flipping. What is that? Is that a bicycle? Is that a, you know, what is it? But that wouldn't happen in a standardized world, you know. So we say, okay, well, I'm seeing there is an issue. So in particular, when several vehicles are communicating with each other, you can actually make it easier. So that's kind of the idea. It will contribute to the overall safety of all the people involved.
Can I because of the competition aspect, that's why in America here that they don't want to have that uniformity.
Yeah, so it comes there, although the US is actually pretty good in standardizing once they want to have the standard. Okay, so it's there is this strong emphasis on competition. But the problem is that if you have 5 OEMs and they all say, I want to have an autonomous car, and the mindset of the CEO is, I need to kill them all, and then I'm surviving, and everybody has to buy one brand, and we would have communism, right? So, I mean, it would be one. So you need to have some form of interaction. And that is the problem they are doing. They are all talking to the government individually, but they have a hard time agreeing on each other because they think, oh, well, I don't tell him this because maybe then they know something more, which I don't want them to share. So what we are doing is we are bringing all the experts together, and they know it anyhow. So nothing can be hidden because we know all the experts. So there is no company that knows more than these 300, 400 experts. So we can then make sure the best practice is already good enough for everybody to agree. That's the idea.
The audience, the group, is there any questions? Okay, you can ask Taiber if you have any question online.
Yes.
Audience.
Yes. You had a question? Yeah.
No, I think if you just, because you don't have any mic.
So you need my microphone or
Yeah,
what?
so-
Yeah, so I'm sorry, I didn't understand that.
So,
So I'm giving you.
no, that's fine.
No, you can-
So is there any question from the online audience? Yeah, please write in the chat box or you can speak up too. I think let's wait and see. Oh, sorry, there's a question.
There's a question. Okay, yep. Yeah, yes, yes.
About software update on the go, which will be a trend, as you were saying, in the next 10 years for the present car. And how this certification safety side can contribute towards understanding software upgrade on the go.
Yeah, that is possible. There's with the software-defined vehicle architectures. So for example, Tesla has this shadow mode where you can already, so for example, software on the go would mean I'm uploading the software before it's actually already used by the user. It's just kind of, it's in the car. Yes, we're checking, is it behaving correctly? And then if it behaves correctly, then you just switch it to the new version. And that can actually happen in real time. Yeah, so
Testing is happening in real time.
so basically the new software is first being tested on the vehicle while the other old version software is still active. And then when everything is good, then it's being switched. So that is in the new software defined architecture is possible. But it's not yet reality for most of the cars. Right?
Not yet.
No.
So it tests all the scenarios on the edge in the car after the software. You need to
All the scenarios that it has to do. So I mean, like you can say this software needs to cover those scenarios, and then you go through all these scenarios. So you can also say, I'm driving in the car, I'm testing the software, and I'm waiting until I have all the scenarios covered. And so 99% is covered. Okay, now I can switch it to that software.
Real mode.
Yeah.
So after the software will now function.
What you cannot do is that you upgrade the car in a safety critical situation while you're driving the car and then have a hot swap of the software. That will not be okay. And the government will not allow it.
So one more
Because that would be
question.
like, you're driving a bicycle, and while you're driving the bicycle, I'm starting to kind of unloosen a screw and then check and then I mean, you cannot do that. Right?
Also, any other question?
just have this question to extend a little bit.
Yeah.
Like just a non-invasive scenario which we normally witness
Yeah.
in websites.
Yeah.
That update, a version update on the websites.
That is possible. So something non-safety related, like infotainment, yes, that can be done. Yeah, that's.
I'm just trying to compare a non-invasive or website development with such a big task of software defined network. If
Yeah.
some component fails, how
Yeah.
can this be prevented beforehand because of the software update?
Redundancy. You need the redundancy in the system.
But if so they will check, right? So if the update doesn't work, the whole system will be operational until we fix the bug.
Okay.
Yeah, any more questions, Jack? Okay. All right, so I think thank you. So then we learned a lot from you.
Yeah, thank you. Yeah.
As I said, you are one of my greatest teachers. So
Oh, well,
thank you.
I'm always glad to be here and learn new things. And thanks for the challenging questions. Okay.
Thank you so
Yeah,
much.
thank you. Thank you very much. Thank you. So,
Thank you guys. Thank you.
hopefully my car's still there.
Yeah, let's see. Yeah. Thank you, Naomi. Thank you.
Good.